qualitative parameters and how they are associated between themselves is one of the interesting subject in statistics. Today we will see two examples, including a chi-square distribution and how do we measure the qualitative association or the association between two qualitative parameters or more than two qualitative parameters called attributes in a distribution. So I have a problem where the problem says, can vaccination be regarded as a preventive measure for a new strain of viral infection from the data given below? So this is a data for a new strain of viral infection where vaccination is ongoing and a sample of 2000 person has been identified, and out of them 450 have been vaccinated, and out of those vaccinated 45 still got infected, and overall we have 550 infected out of the whole sample of 2000. So how do we solve such kind of problems? This is what we will discuss and I will show you subsequently. So we'll get back to this problem later on. Just wanted to show you what kind of the problem we want to address today. Next problem is now the company is interested in determining the strength of association between the commuting time and the level of stress. So we have a qualitative data which represents stress factors or the stress values, high stress, moderate stress or lowest stress among the employees, and the other attribute that we have is the commuting time, the time the workers take to reach to the office. So these we have in this example the commuting time and the stress as two of the attributes, and they have their own further classes subdivided into their three different classes for each of these attributes. And how do we address these kind of problems in the world of statistics? And the important thing is I will show you the whole plotting in R. So to start with, I thought I will just quickly walk you through some of the fundamental mathematics behind this. So I'm not going into the details, but I'll quickly walk you through the slides so that you understand what is the underlying foundational mathematics that these kind of calculations are using. So when we talk of attribute classification or the qualitative variables, it can be classified as either dichotomous or the manifold classification. So with dichotomous, it means you have an attribute with two classes, and the example, the first problem that we discussed, that I showed you, we haven't discussed yet, is an example of dichotomous classification, this one. So you have a vaccination as one of the attribute and infection as the another attribute in this example, and this is basically you have more than two classes for this second problem, which falls under the manifold classification. So to understand what exactly are attributes, if you have to compare intelligence versus honesty in a group of people, or education versus crime rate, maybe it, in a city or a locality or a country or a province or a state, or and so, and what is the association between income and the graduate degree? Does your degree affect your graduation, your income? So this kind of questions are addressed using the method that we'll be discussing. So this is the mathematics of dichotomous classification as well as the manifold classification. So the symbolic representation AN, what what this says is if we have an attribute called A and we have an attribute called B, an attribute called C. So these are three different attributes, right? A could be honesty, B could be intelligence, and so and so. So there A will have its own complement of an attribute which is complement of it. So when I say A is honesty, then A complement is not being honest, right? So symbolically they are represented. A complement is represented as alpha, or B complement is beta, C complement is gamma. So that's the symbols being used, or the syntax being used in the statistical books. So when we say bracket A, it means the count of A, the count of people who are honest. For example, let us say A represents the people who are honest, then bracket of A, and AN, we say AN is equal to bracketed A. So N is the population size, or the complete or the count of all the frequencies for that particular sample, right? So the total value is N. So AN we say bracketed A, and we say alpha N is equal to bracketed alpha. So alpha is just opposite of A, beta N, beta is just opposite of B. So when we say B represents people who are intelligent, beta represents people who are not intelligent. So that's how it is being categorized. And here is the maths that we have. So we will be using the formula alpha into beta, or alpha beta. That means if I take A as people who are honest and B as intelligent, then alpha beta means people who are neither honest nor intelligent, and that formula is N minus A minus B plus AB. Okay, so that is the formula. We'll see how it how we can relate it to a real example. And alpha beta gamma would again similarly would be N minus A minus B minus C plus AB plus BC plus AC minus ABC. So this is how it looks like. So I would suggest you go through any statistics book so that you grasp these concepts. I'm not going to teach here, just wanted to show what are the methods that underlying methods that are being used. So when we now coming to the consistency conditions. So if you are given with a sample, some data distribution, how do you test whether that sample is consistent or not? Does it make sense actually whether the data is consistent? So these are the consistency tests. We are not going to do it here. I thought of showing you. So obviously the count of A should be greater than equal to 0, and alpha should be greater than equal to 0, and so on. So not going to discuss in details about this. The condition 2 is AB should be greater than 0. Otherwise AB would be negative. So negative frequency for people who are honest and intelligent, it cannot be negative, right? It has to be greater than equal to 0. So these are the consistency methods that we normally use to check whether the data that is given to us is consistent or not. So in the real world, when you get the data first, you check the consistency, and then you apply the association rules to check what is association, whether you are applying the dichotomous association rule, or you want to apply the most popular chi-square distribution, or chi-square test, or chi-square goodness of fit. Now we will take an example, our problem 2 that I showed you. We'll solve it in chi-square later on. So these are the consistency conditions, and these are again the consistency conditions if you have 3 attributes or 3 variables. Variable in the sense that the attributes, okay, these are not the normal variables that we're talking about. We're talking about the 3 attributes. The variables, you have a set of random variables, but you have 3 attributes, right? So again, I'm not going into the details, and this is the criteria to check for attribute independence. So if I have 2 attributes, a dichotomous classification, so AB divided by n is equal to A divided by n into or multiplied by B divided by n. A bracketed AB, bracketed B represents the frequencies of that particular class. AB is the class which has both attributes, and bracketed AB is the frequency of the class that has both attributes, right? Similarly, bracketed A is the frequency of the class that has an attribute A. Bracketed B is again the frequency of the class with attribute B. So this is what we test for independence as independence, and whether the attributes are independent or not, and what are the and what kind of association they have, whether it's a positive association, negative association, or no association, right? Interesting thing is we'll talk of the Yule's coefficient of association, and this is what we are going to use it. So far I understand that I have quickly discussed the previous subjects, the underlying topics, because the idea is not to teach statistics here. But Yule's coefficient of association is actually the degree of association between these qualitative variables. So how far these qualitative variables are associated between themselves, or the attributes associated between themselves, is the Yule's coefficient of association. And we know what A and B are, what alpha and beta are. So this is the formula which is used, and if the coefficient of association is 1, then it is a perfect positive association. If it is -1, it is perfect negative association. If it is 0, then the attributes are independent. Now we will talk of the problem, the first problem that we started, I showed you in the starting of this video, and the problem that we started with this. So here is the problem. Now we understood this is the formula for calculating the coefficient of association, and we understood what exactly are the symbols A, B, C, alpha, beta, gamma. So we'll try to relate it in a dichotomous classification, where we say 2000 persons, so people in a locality, got exposed to a certain viral strain, or it says a mysterious virus or a new viral strain, and 550 of them got infected, right? But out of 2000 persons, 450 had been vaccinated, and of these only 45 were infected. So based on this data, the pharmaceutical company wants to decide during a clinical trial whether this vaccine is good enough. Is there a negative association between the vaccination and the infection? Should we continue with the commercialization of the vaccine? So how to do it? It is very simple. So this is the way we do it. So we know that the frequency of a attribute of vaccination is 450. We have, if you see the question, it says 450 had been vaccinated. So A is 450, B is the frequency of B is number of people who got infected as 550, N is 2000, total frequency. AB is 45, because it says only 45 were infected despite vaccination. So out of the number of people who were vaccinated and then got infected, it is AB, capital A, capital B, bracketed 45, and alpha beta is the people. If you see, what is alpha? If A is number of or frequency of vaccination, alpha is people who are not vaccinated, and B is if the frequency of infection, beta is people who are not infected. So people who are neither vaccinated nor infected is alpha beta. So we have used alpha beta, this formula. If you remember, I showed you this formula, alpha beta, and minus A minus B plus AB. That's the reason I showed you quickly these formulas. And we derived the value of alpha beta, frequency of alpha beta 1045. Similarly, vaccinated but not infected is A beta. So A minus AB, that is 405, not. And if you see vaccinated but not infected, A beta, similarly is A is vaccinated, B is people infected, so beta is obviously not infected, so it is A minus AB 405, and so on. So that's the calculation part. Now we derived, if you see the formula, we need to find AB, alpha, beta, A beta, alpha B, AB, alpha beta, A beta, alpha beta. So all these values we found out and we put it in the Yule's coefficient of association, and the value comes out to be negative 0.62612. So any negative value more than 0.5, any value whether it's positive or negative, it is more than 0.5, it shows a strong association. But since this is a negative association, high degree of negative association between the two attributes, vaccination and infection, so it can be inferred that this vaccination can be considered as a preventive measure for the virus. So the pharmaceutical company should go ahead in a mass production of this vaccine. So this is the very basic model of a dichotomous classification, and similarly the way it is being done is a 2x2 contingency table is being designed for this kind of classification. So this is 2 multiplied 2 or 2x2 contingency table for dichotomous classification, where you have both the attributes in both the axes, on the vertical and horizontal axis, and you have the combinations, and this is how it is represented actually. And this is not just for 2x2, it can be for any kind of any dimensions of the attributes, or the class of the attributes. You can have a contingency table even for a manifold classification. So there is another coefficient of colligation, which is also sometimes used in understanding the association or the degree of association. So we are not going to solve this here. I just wanted to show you how to build on these kind of fundamentals. Now for manifold classification, we have, instead of 2 classes, an attribute can be classified into number of classes, as I said. Something like we have 2 attributes, say popularity, and a popularity for, say, film star, or popularity for a celebrity. It can be classified into less, medium, high, extreme, or a stature, very tall stature, medium, short, very short. So just instead of having 2 classes, an attribute can have multiple classes, right? So that is called manifold classification, and this is where chi-square test is so important, and we will deal with one problem that I showed you initially. So for manifold classification, if we say we have an example, say we have 2 attributes here, A and B, but then they are subdivided into multiple classes. So A is subdivided into R classes, B into S classes. So when I say R classes, it is like the popularity here is, if we say is less, medium, high, and extreme, then it is 4 classes, right? Similarly, stature is tall, very tall, medium, short, very short. So we have 5 classes. So it is like 4 by 5, 4 cross 5. So here we have R cross S, and we have R classes for attribute A, and S classes for attribute B, and this is how the contingency table is represented. This is the method that we use in breaking down a problem, or the problem itself can be given to a statistician in the form of contingency table as well. So it depends on the scenario, and this is how it is being represented. And you can see the total number of frequencies, total frequencies for class B1 is A1 B1, A2 B1, like AI B1 or AR B1, and so on. So the rightmost column represents the frequencies of the class B for the individual subclasses of attribute B for the individual subclasses, and the lowermost row represents the frequencies of attribute A for the subclasses, right? And then this is the expected frequency. Why it is important, why I showed you this is These are the observed values of the values from the observation. You'd go and do a polling or something like we spoke of the vaccination. So you have an observed value or the experimental value that you got. Now, what is the expected value? What should have been the expected value is now the expected frequency table here, and this is how it is calculated, right? And this is what is important. This is important because the observed minus expected and the square of that, and we take that difference as an input in the chi-square test. So if A and B are completely independent of each other, then the values A1, B1, A2, B2, etc. must be equal to the corresponding expected values. So in this case, if A and B are completely independent, if the attributes are not associated with each other, these are qualitative attributes, parameters, where they're not associated with each other, then the expected and observed must be same. So that is what it is saying, right? So these are all the independent attributes, properties. So in the second property says if observed frequency of each cell of a contingency table is equal to the expected frequency of the same cell, then we can say and B are completely independent. That's fine. That is the something derived from point number 1. So if these values are not equal for any of the cells, then it indicates association between attributes A and B. So again, it is the same derivation from point 1 and 2, and point 4 says in order to measure the level of association, the difference between the observed and the expected frequencies for various cells are calculated. With the help of such differences, the value of chi-square is calculated, which is abbreviated as chi-square. So that is fine. So this is the notation for chi-square. So that's the whole idea is to build the mathematical model for chi-square, and that is what I wanted to show you and plot in R. And this is the chi-square formula that is being used for the classes R, and for the first property, first attribute having R class, second attribute having S class. So difference of observed and expected frequencies, the square of the difference divided by expected frequencies. And this is the chi-square. Again, the same thing. We are saying the observed minus expected, square of that divided by expected over the class of the complete class of attribute A and B, the summation, right? And the same thing here. So chi-square is also known as square contingency, and there is another term which we're not dealing here, that is called mean square contingency, or chi-square by total frequency, or chi-square by n. So anyway, let us move to the coefficient of mean square contingency. So this is the coefficient, something if you remember, we found out a coefficient, Yule's coefficient, for a dichotomous classification. So this is something you can relate that to with a chi-square distribution, where this is the coefficient of mean square contingency, or in terms of chi-square value or in terms of the phi square value. So now why this is important is I will show you. Suppose this is the chi-square formula that we discussed, right? Chi-square is the summation of this particular value formula and this formula. So suppose we take S as the summation of observed frequency square by E, then the coefficient of mean square contingency can be written as square root of S minus n by S. So this is very important. The reason is when we say, suppose this terminology is represented as S, then the coefficient of mean square contingency can be represented as square root of S minus n by S. The reason why this is important is this value is dependent on the number of classes an attribute has. So if you see the limit, if you find out the limit of C, it will reach a limit of 1 only if there are infinite number of classes. So that means R and S values are huge. So for a particular value of or the order of the classes or the distribution, the coefficient of coefficient of mean square contingency will be varying. So the maximum value, let us say if I have an order of 3 by 3, So I have two attributes of three classes each, subclasses each. So the maximum value of C will be square root of 3 minus 1 by 3. So it is square root of 2 by 3. So this is important when we have to relate the theoretical maximum value of the coefficient of mean square contingency with the observed value. I will show you in an example. Now we are going back to the first problem, second problem that we started initially with that the company wants to find out the association between the commuting time of their employees and the level of stress so on job, and they have done the study on 116 assembly line workers. So typically these are the assembly line workers are in the production shop, and they and various level of stress were noted in these workers. So the company wants to find out, is it because of the commuting time? So they had a data of 116 assembly line workers classified into two attributes with three subclasses each. So this is the data or the observed data from the observation that we have here. Now if we go to the contingency table that we discussed, so we can find out the expected frequency of each cell in the from the contingency table. You can create a frequency contingency table here, and theoretically you can calculate, it's not a very complicated thing. You can calculate the values of chi-square here. For example, for the cell which has A1 B1, the observed frequency is 9, but the expected frequency is A1 into B1, that is 32 into, that is complete B1, complete A1, the frequency of whole B1 subclass, frequency of whole A1 subclass, that is 32 multiplied by 44 divided by the total, and total frequency is 116. So similarly you can find out the frequencies, and you can get us chi-square here, the total value of all these differences, and summed over all these attributes you get the value of over all the subclasses you get the value of chi-square. The problem here doing manually is there are chances of rounding errors, and you will tend to round the errors, and you may get a wrong picture of it, and if the values are big, then it will become difficult to do it manually. So in my case I would not recommend to do this manually at all. I wanted to show you this solution in R. So in my case I did some rounding off, and I ultimately found a wrong value of chi-square. So I'm not going to discuss it further here. We will build it using R, and I'll show you how we can do it. So then finally we can draw an inference. So how from this chi-square test, let me go to the studio and let us try to solve this. So make sure that you first have these three libraries included. We will be using ggplot2, reshape2, and coreplot2. The main functions to interact with the chi-square distribution are these are the functions: d chi-square, p chi-square, q chi-square, r chi-square. So you can have a lot of observation using these functions. You can go and read the manuals or help for these particular functions. So now I have a matrix called A, which represent these three. If you see the matrix here, this is the one which has high stress, moderate stress, low stress, and fast commuting, average commuting, and late commuting corresponding values. So this is the matrix I built here. let us now use our further test. So we will go for the we'll first go for the chi-square. This is the function that you use for chi-square test. So this is the function you use. I'm putting this in a variable called test. So, and let us see what test shows. So test shows that this is the value that the test is showing us. So the chi-square, the a square, that is the chi-squared value is 9.8311. Straight away it is finding out. With the degree of freedom is 4, because we have a 3 by 3 subclasses. So 3 minus 1 into 3 minus 1, 2 by 2. So now it is degree of freedom is 4, and the p-value is 0.04337. It is lesser than 0.05, so it is good enough. So I will show this with a different p-value as well, and with a different percentile, and with a different what is the expected. This is the observed chi-square value that we have. What is the expected chi-squared value? We can find out. So let me show you what is the expected chi-squared. Okay, so this is what we have now. So if you see this particular variable, when you run a chi-square test, so you have an observed set of values also, and you have an observed as well as expected value, right? So obviously the observed is what we had, and if you try to find out the expected, you will get the same one. Now, let me show you the expected values. So this is the expected value. This is what is expected. This is what is observed. This is the observational value, and this is the theoretical expected value for a chi-square distribution, right? So what I have done is actually I have rounded the expected value for the calculation part. Okay, so let me and showed you this one, but again I'm not using the round in the calculation as such. I just rounded to show you in terms of, because a person cannot be a 12.13 and 5.24 and 8.68, right? The person, it is difficult to have a decimal value and the frequency when the frequency represents the count of people. So that is the reason I did not want to solve it manually. So because in the manual solution, when you round it, the value becomes distorted. The different value comes up. So I want to use it completely with the same value and find out whether it is a right. There is a significant degree of association between the stress factor and the commuting factor, or the commuting attribute and the stress attribute. So I wanted to show you one thing here. So this is in particular, let me just go to this particular function, and rather than plotting the graph right now. So if you see, as I said, there are certain functions which are important in chi-square. So this is one of the functions. So what it says is the 95. This is the 95th percentile of chi-square distribution with a degree of freedom 4. This is the 95th percentile, right? When we are saying this is what is expected value. So the expected value of chi-square is 9.487729, and our value which is coming is 9.8311. So the expected value is 9.49. So you can also see this in a chi-square distribution chart for a particular degree of freedom. So there is a chi-square distribution, standard chi-square distribution chart, where these values are called the critical value for chi-square with p-value 0.05, that is 95% probability, and degree of freedom 4, 3, 6, and all the various degrees of freedom. So this is what we calculated here instead of remembering the chart. So the value should be, ideally should be either less or equal to 9.48. In our case, the value comes out to be, as we have seen in our case. Now let us run once again the test. In our case, the value was 9.83411, but it should be 9.48, so it is more. That means the association is not significant between these two attributes. So we cannot clearly say that the stress is due to the commutation. So that's the logic here, right? So if I have two hypotheses, the null hypothesis say yes, there is a strong association between the stress and the commuting time, and alternate hypothesis says there is no association between the commuting time with the stress. So we reject our null hypothesis and our alternate hypothesis is correct. Okay, so quickly I will show you some of the interesting charts here that you can plot here. So there are a lot of values that you can see, the observed, the expected, which I showed you. This is one we can plot. I don't want to plot this, so let me plot this particular not be plotting this. Okay, so let me plot this. So one of the interesting thing before we plot this is one of the interesting variable is the residual variable, right? This is the residual, the difference between the observed and expected. So if you print this, you get this difference here, and you can plot the residual and see what kind of correlation. I won't use the correlation, the association is there between the two attributes. So you can see the blue one shows a strong positive. The shape of these balloons or the circles actually represent the degree of association, and the color represents the slope of the association or direction of the association. That means if it is blue, it shows positive association. It is red, it shows negative association. So if you see the high stress late commuting time has a very positive association, lowest stress and the late commuting time has a very negative association. So we can see from the residual, this residuals also. So high stress and the late commutation shows a very positive association. This shows very negative association. So we can plot a residual plot as well. And also, you know, if you want to see, let me do this one as well. And the same thing, if you want to convert it into a percentage. So this is the residual plot that we have done. Now if you want to see the percentage, the contribution of a given cell to the total chi-square score. So each cell contributes in the contingency table, each cell contributes to the total chi-square value, right? So what is the contribution of each cell? And if you want to plot it and visualize it, then also you can do it. So the contribution is equal to r square divided by chi square, where r is the residual of the cell. So each cell, this is the residual. If you see this particular below in the console, let me show you once again, test residual. Let me highlight it. So this is the residual, right? Now what is the contribution of each of these cells to its overall chi squared? So the contribution is equal to r squared divided by chi squared. So that's the formula, and we have used this formula here. It is just another way of representing, so don't worry about it. It is just another way of representing. So we have converted this into a percentage. So if you see this particular line, so contriv is a variable I have taken. I have calculated it in terms of I made it 100 into test residuals square, divided by test statistics. So okay, so let me show you what is test statistics so that you will also appreciate what I'm trying to tell you. So this is the test statistic. So this is the chi-square value, right? So as I said, the contribution of each cell is r square by chi-square. So the percentage contribution will be r square by chi-square into 100. So that is what we have done it, and we have rounded it, and then we have plotted it here, right? You can do it in that way. You know, you can make it contrary, and let me put the rounded value here. So I will plot it. So this is the contribution of you can see the contribution of each cell to the overall chi-square. So you can see the late commuting with the high stress and the late commuting with the low stress is the most contributory factor in the chi-square, and which we have also seen in the previous core plot. So to construct this kind of core plots, we have included the library that I showed you in the beginning. So this is the library that you need to include, library core plot. Fine. So this is like this. You can have as many number of plots that you want. You can explore more on this. The other interesting thing I wanted to show you is why I use the reshape library is the original distribution that we were given with for A. So this is the distribution we had, right? The original distribution. This is the distribution we had. Now if we had to plot it in a graph, the distribution itself, so this is the method you do it. You need to include a library called reshape2, and then there are certain functions that are used. What I have done is I have converted this into a table and used a melt function. The reason is I want to convert the data into a long form. I'll show you how it looks like. So this is the value A. Now I've included the library. Let me run it. Now I've converted this dt. Now I'm using melt dt, and now when I run this particular balloon melted, my new variable, this is what it means in a long form. This is a long form of the data. There are two variables. It says var1, var2. There are two attributes or variables, and this is the auto naming where the function itself names it, and this is the value. So if we use ggplot, we can use the plotting using a long value, not using the plot, or not using the distribution the way we had it initially. So now with this long value, you can plot the distribution. So this is the distribution. This is the plot, and we are using balloon melted. That means this particular variable and a long format to generate the plot. This is the plot that we generated. So here you can see there are two variables, variable 1, variable 2, and you can see this is the observed, this is a plot for the observed values or the observed distribution, which we had in the question or the problem itself initially. So you can see the shape of the circle represents the degree or the value that we have in the observed frequency table, right? So these are the various ways you can plot a graph. So in general, the idea was to show you that the chi-square value here is more than the value of the critical chi-square value, or the expected chi-square value, we can say, which we have seen. So this is not a we cannot consider that these two attributes are associated, and so we can we can turn down the hypothesis, the null hypothesis, that they are significantly associated with each other. So this is what I wanted to show you all in today's video, and hope you would appreciate the various graphs that we plotted and the fundamentals, and you can keep on doing more exercises and more plotting. There are various ways to plot it. There can be a power plotting, advanced R plot, graph plotters. So these are the very basic things I thought of sharing with you, and thanks for watching this video. Thank you and bye.